In this video, we're going to talk about the photoelectric effect, a massively important experiment that provided the evidence that Albert Einstein needed to propose that light behaved in a particle-like manner as well as in a wave-like manner. So what does this experiment look like? What you can see in the diagram before you is an experimental setup. We have light shining on a metal rod, which is what we see here. And if the light has sufficient energy, then it ejects electrons from that metal rod, creating a current. It's also possible to apply an external potential to the system, and that external potential essentially provides energy pushing back against the electrons. And so it's possible to measure the size of potential required to completely stop the current, to stop the electron flow. And that is referred to as the stopping potential. And that is how we are able to measure the energy of the electrons that have been ejected from the metal by having the light shone on the metal. Now, prior to Einstein's conclusions, which stemmed from this experiment, people believed that light acted as a wave and logically, therefore, that it only acted as a wave. So let's think about what you would expect to see in this experiment if light really truly only did behave as a wave. So we're shining light on a metal rod. I've redrawn that diagram up in the corner of your notes here. And let's say, for the sake of argument, that no current flows. There's not enough energy to eject any electrons. Well, what should happen if you shine a brighter light? Well, you would expect, if light only acted as a wave, and the energy of the light was therefore proportional to the intensity of the light, that by shining a brighter and brighter and brighter and brighter light, you should eventually be able to induce a current to kick electrons out of the metal, and that as you shine that brighter and brighter and brighter light, and you have more and more and more energy being carried by the light, that the electrons should be ejected with more and more and more kinetic energy. So you would expect increasing the intensity of the light to increase the energy of the electrons. Turns out that wasn't what happened. We can see what actually happened in this graph at the bottom of the page. So here we have the x-axis showing frequency, because of course I just drew right over the nice neat typing of the word frequency. And on the y-axis we see the current, the number of electrons ejected from the metal. And we can see two lines here, a low intensity light in dotted line and a high intensity light as the solid line. So low intensity light, that's the dim light. High intensity light, that's the bright light. At certain frequencies, we saw very little current, essentially no current here. And then we hit a magical frequency right here that we will call the threshold frequency. And so for light that had a higher frequency than that threshold frequency, we can see a significant amount of current being induced by shining the light on that metal rod. Below the threshold frequency, little to no current. The kinetic energy of the electrons actually doesn't change. No matter how bright a light you shine, at the same frequency, the electrons are ejected with the same energy. The energy stays the same. What does change is the number of electrons ejected, as evidenced by the increase in current. For those of you who aren't so familiar with these terms from physics, current is essentially the number of electrons flowing per unit time. So shine a brighter light, you get more electrons, but they have the same energy. And that's not consistent with what you would expect from the wave model of the light. So as we saw on that diagram on the previous page, intensity of the light wasn't the only thing that was varied. Frequency of the light was also varied, and the current only flowed above certain frequencies. On this graph on this page, what we're seeing again is frequency on our x-axis. And on our y-axis, instead of current now, we're looking at the energy, the kinetic energy of those electrons. Now, if light acted as a wave, there's really no reason that the frequency of the light should have anything to do with the energy of the ejected electrons. So you wouldn't expect there to be any significant change or any significant relationship between frequency and energy of the ejected electrons if light was just a wave. But this graph here shows us that there is in fact a very clear relationship between the frequency of the light that was used and the energy of the electrons that were kicked out. This solid blue line here, that's your experimental data. And again, we can see that we have that threshold frequency, which was required for current to flow at all. Below that, no current flowed. You can't measure the kinetic energy of electrons that aren't flowing. And so there was a linear relationship there between the kinetic energy of the electrons and the frequency of light that was used. The slope was equal to Planck's constant, which I will have nicely spelled out on a future slide, but the symbol for that is this lowercase h. So the energy of the ejected electrons is increasing as the frequency of light increases, and it's a linear relationship. So this was also inconsistent with the wave model of light. And so Einstein was the one who was smart enough to take all of this experimental data and come up with an alternative model for the way in which light was behaving in this experiment. And what he suggested was that the light was essentially functioning as tiny little packages of energy, which he termed photons. And so if a photon of light struck an atom with sufficient energy to eject an electron, then it did so. And if the package of energy did not contain enough energy to eject an electron, then it didn't. The electron was not kicked out. If the photon struck the atom with more energy than was needed, some of that energy was used to kick the electron out, and the rest was carried off with the electron as kinetic energy. He concluded, based on the graphical evidence, that the frequency of the light was actually directly proportional to the energy of the light. And this relationship is expressed using Planck's equation, because we saw that Planck's constant was the slope of that frequency versus energy graph. And so we are able to say that the energy of a photon is equal to Planck's constant times the frequency of the photon. So that means then that even if you shine two equally bright lights on the metal, if the light has different frequency, it's possible that one will induce a photoelectric effect and one will not. And that comes down to the amount of energy each of the individual photons in the beam of light is carrying. So you might have one light beam that has a lot of low energy photons and one light beam that has a smaller number of higher energy photons. And if there is not enough energy being carried by the photons in the long wavelength, low frequency beam of light, it doesn't matter how many of them strike the surface of the metal, the statistical likelihood of 2 or 3 of them striking exactly the same atom at the same time so that their energies could all combine and be absorbed at once is extremely low. And so you don't observe a current. I've got a graphical representation of that at the bottom here. You can see two waves of equivalent amplitude, equivalent intensity, but the one on the left has a much shorter wavelength. And you will recall that frequency is the number of complete cycles of a wave that can pass through a given point in a given unit time. If each complete cycle is shorter, you're going to get more of them through past that point. So shorter wavelength, therefore higher frequency, and therefore higher energy compared to the longer wavelength, lower frequency, and therefore lower energy wave drawn on the right. If we want to calculate the threshold energy for a metal, the minimum amount of energy required to kick an electron out of that metal, we can do so by shining a light on the metal that is high enough in frequency and therefore high enough in energy to be able to induce a current, and then measure what the kinetic energy of those electrons is. I already mentioned this idea of the stopping potential. Measure how much potential is required to stop those electrons. If we do that, we are then able to calculate the minimum energy required to eject an electron. And I will tend to refer to that as threshold energy because I think the relationship between threshold energy and threshold frequency is a lot clearer using that terminology. However, if you are a physicist or an engineer, you should get used to the term work function, which means exactly the same thing. It's just another word for the same thing. So threshold energy and work function, essentially synonymous. Like I said, the reason that I personally prefer the term threshold energy is because then the relationship between the threshold energy and the threshold frequency is much clearer. We can use Planck's equation to relate between the two. The energy required to eject an electron from the metal is equal to Planck's constant times the observed threshold frequency. So how do we calculate all of this? Well, in this question, we've actually been given the threshold energy of zirconium. Now note that we have been given this in kilojoules per mole. So this is not the energy required to eject one electron from one atom. This is the energy required to eject 1 mole of electrons from 1 mole of atoms. So the very first thing that we need to calculate is the energy of a single photon, the lowest energy a photon can have in order to induce a current in this zirconium sample when it's put into a photoelectron effect experiment. So the threshold energy in joules. We have 391 kilojoules per mole. We, of course, want to convert that into joules, but that's pretty easy. We know there's 1,000 joules in 1 kilojoule, and then the kilojoules cancel. Now, how do we get rid of the moles? Well, in 1 mole of photons, there are 6.022141 times 10 to the 23 photons. And that's Avogadro's number. There are Avogadro's number of atoms in a mole. There are Avogadro's number of molecules in a mole. There are Avogadro's number of photons in a mole. And if you really, really want there to be, there are Avogadro's number of chickens in a mole. It doesn't matter what we're talking about here. Whatever the subject is of interest, there's 6.022141 times 10 to the 23 of them in 1 mole. And so our moles cancel, and that gets us a threshold energy of 6.49 times 10 to the minus 19 joules per photon. Now that we have calculated the minimum energy of light that can induce a photoelectric effect, and we have it in joules per photon, we can use Planck's equation to calculate the minimum frequency of light that can induce a photoelectric effect. So we know that the energy is equal to Planck's constant times the frequency, threshold energy, threshold frequency, and therefore the threshold frequency is equal to the threshold energy divided by Planck's constant. So 6.49 times 10 to the minus 19 joules, all divided by 6.626070 times 10 to the minus 34 joules per hertz. Now, you will oftentimes see the units for Planck's constant written as joules times second, because if you want to reduce to the minimum IUPAC units, joules and seconds are base units. However, those two sets of units are completely equivalent, and in the context of this question, my friendly local physicist assures me that it makes much more sense and is much more intuitive to report Planck's constant in joules per hertz, because look at what we're doing. We're taking an energy in joules and converting it into a frequency in hertz, which is 9.80 times 10 to the 14 hertz. So how can those possibly be equivalent? Well, remember what 1 hertz means. 1 hertz is 1 cycle per second, but again, in the IUPAC base units, you don't see the cycle, so therefore, you would also say 1 hertz is equal to 1 second to the minus 1, or 1 inverse second. Now, if we take those units then and plug them into that joules per hertz, we are saying then joules per inverse second, and anytime you divide by the inverse of something, you are essentially multiplying by that thing. So joules divided by inverse seconds is the same thing as joules times seconds. And so you can write Planck's constant in joules per hertz, or you can write Planck's constant in joules times seconds, and they're perfectly equivalent. Again, we're only going to give you one of those two sets of units on your formula sheet, but you should be able to convert back and forth between the two, and you should be able to answer any question starting with either set of units. So start with whichever set is more convenient for your particular question. So now that we've calculated the threshold frequency, we can go ahead and calculate the threshold wavelength, or the maximum wavelength of light that can induce a photoelectric effect in zirconium. Remember that as frequencies get bigger, wavelengths get shorter. So instead of a minimum wavelength, it's going to be a maximum wavelength. But we know that there is a relationship between frequency and wavelength, which is that they multiply to give the speed of the wave. And in this case, our wave is light. So speed of light equals wavelength times frequency. We know our frequency, we're solving for our wavelength, so therefore we can rearrange our formula to say that wavelength is equal to speed of light divided by frequency, which is 2.997925 times 10 to the 8 meters per second, divided by 9.80 times 10 to the 14 hertz. And as we just saw above, 1 hertz is equal to 1 inverse second. So you can either write that as second to the minus 1 or 1 over second. The inverse seconds cancel, the hertzes cancel, and that gives us a wavelength of 3.06 times 10 to the minus 7 meters. However, oftentimes we would like to report distances in units that don't require scientific notation to report. So if I convert this into nanometers, I can report this as a number without invoking scientific notation. To do so, I multiply by 10 to the 9 or a billion nanometers in 1 meter. And that gives me 306 nanometers after my meters cancel. Now, I'm going to strongly recommend that when you do unit conversions, you take the approach that I've just taken here, which is to actually write out both the units you're converting from and the units you're converting to and make sure they cancel. I know there are tables out there that say to go from this to this, multiply by a billion. To go from that to that, divide by a billion. And I cannot tell you how many times I have seen students accidentally divide when they meant to multiply, or accidentally multiply when they meant to divide. If you do it this way, you can't possibly make that mistake, because if you have your conversion factor upside down, stuff won't cancel. And so our last question relating to the photoelectric effect, our last calculation here, we are to take the sample of zirconium we were talking about on the previous page, which had a threshold energy of 6.49 times 10 to the minus 19 joules, and calculate the maximum kinetic energy those electrons could be kicked out with. We've been given the wavelength of the light that's being used in this experiment, so we can use that to then calculate the energy of the photons of light that are being used in this experiment, because what we're going to want to be able to do is plug values into our equation relating the threshold energy, or work function if you prefer, and the released kinetic energy of that electron. So we have threshold energy. We're solving for kinetic energy. That means we need energy of the photon. So to calculate that, we know that the energy of a photon is equal to Planck's constant times the frequency, except we weren't given the frequency. We were given the wavelength. So we also know that the speed of light is equal to the wavelength times the frequency, and therefore the frequency is equal to the speed of light divided by the wavelength. And then we can take this over here and plug it in for frequency, and that gives us energy of our photon equal to hc over lambda. Many of you will be familiar with that equation from physics. We don't put this equation on the formula sheet because we give you Planck's equation and we give you the speed of light equal to wavelength times frequency, and we expect you to be able to combine these to make the combined formula. We give you all the basic formulas you need to be able to manipulate them. I then plug in my values, so I have 6.626070 times 10 to the minus 34, and this time around joules times second is going to be more convenient, times 2.997925 times 10 to the 8 meters per second, all divided by 225 nanometers. My seconds cancel. Meters and nanometers do not cancel, so I need another conversion factor here. There is 1 meter equivalent to 10 to the 9 nanometers, a billion nanometers in a meter. Now the nanometers cancel, now the meters cancel. Throw all of that into my calculator, and I get that the energy of the photon is 8.83 times 10 to the minus 19 joules. And from there, since the energy of my photon equals the threshold energy plus the kinetic energy of my electron, because essentially the energy of that photon is doing two jobs. It's ejecting an electron from the atom. The energy consumed by that is the threshold energy, and then the leftovers get transferred as kinetic energy. So that means that my kinetic energy of my electron will be equal to the energy that the photon started with minus the energy that was used up ejecting that electron, or the threshold energy, equals 8.83 times 10 to the minus 19 joules minus 6.49 times 10 to the minus 19 joules, and that gives us 2.34 times 10 to the minus 19 joules. When I'm doing my quick mental check as to whether or not my answer makes sense, this is a positive number. That means it was actually possible to eject the electron and there was some leftover energy, which makes sense given that we used lower wavelength, shorter wavelength light in this example than the wavelength that corresponded to the threshold energy, than the wavelength that corresponded to the threshold frequency. If I had gotten a negative energy, that would have suggested that my photon did not actually have enough energy to kick an electron out of the metal, and that in fact no photoelectric effect was induced. It's not possible to kick out an electron with a negative energy. So my answer makes sense. I'm happy with it, and I hope that this example has shown you a better understanding of how the different pieces fit together in the photoelectric effect experiment.